okay? Concentrate and focus, okay? And so we're going to talk about stuff, and then at the end you can just write down the formulas, but I really want you to see where these come from. So my job's going to be so that you can understand where they come from, so that's where the focusing part comes in. And then at the end you can write down the information that you need from that, okay? So far all of our trigonometry has been in right triangles, okay? But it would be nice if there was something then that we could relate to triangles that are not right triangles. Okay, and we clearly can't set up like, oh, the sine of an angle in a triangle that's not right is the opposite over the hypotenuse, because the hypotenuse is across from a 90-degree angle, so that doesn't really make sense if the triangle doesn't have a 90-degree angle. Okay? But maybe we can build a different relationship. So what we're going to see here is we're going to see different ways we could calculate areas of triangles, which you've technically done before, just not in the formula way that we're going to look at it, but you've probably figured the same thing out before. And then we're going to see how we could transform those formulas into a relationship for triangles that aren't right, that do use some trig functions. Okay? So let's say we have a triangle, a non-right, just random triangle. Okay? And it has angles A, B, and C. Way too thick to write with. Okay. Then if you guys were asked to find the area of a triangle like this, okay, and it doesn't have a right angle, what would you do in order to figure out the area? No? 1/2 base times height. Okay, so you do 1/2 base times height. So that's our formula. So we have our area formula. 1/2. I know I'm going to write the words. I'm going to write them to not be confused with some other variables later. So in this triangle, since it doesn't have a right angle, how would you guys establish base and height? Cody?
Make a right angle.
Okay. Good. A line. Does anybody know what we specifically call that line that comes down and makes a right angle with the other side? Do you remember from geometry? We'll just throw it out there. Altitude. Okay. So we'll draw in an altitude. Makes sense, right? In a plane, you have a certain altitude, like your height off the ground. Okay. All right. So we draw this in. This is going to give us our height of the triangle. If that's our height, then I'm kind of establishing that this length down here of the triangle is the base, because those are the two perpendicular things. I'm going to call it B, not because it's the base. I'm actually going to call it B because it's across from angle B. Is that okay with everybody? All right. So oftentimes, to help eliminate some of our confusion in these triangles, we label the angles with capital letters, and then often the sides across from them with the same letter in the lowercase form. So I'll go ahead and call this side A and this side C. Okay? All right, so now if I wanted to find the area by doing 1/2 base times height, if I plug in the variables we have, right now side B is our base, and our height is that altitude that we marked that I called H. Okay? But if I was only originally given these measurements, okay, or some of the angles in here, I might still be stuck. I want to think about a way to rewrite H so that it's not its own variable H, but instead it's based on A, B, or C. Angle A, B, or C, side A, B, or C. I don't care, but something that was given to me in my original triangle. Okay? So if you guys were in this situation and you had to find this height right now, given some of the other measurements of this triangle, the sides, the angles, how would you go and figure out this height? If you had the other sides and the other angles of the triangle, how would you go and figure out the height? Allison?
Would you do like, I gotta read the name, but if you have like angle C, you would do like opposite over hypotenuse.
Good.
And then
That's exactly it. Yep. So if we had the measurement of angle C, we could figure out H by using kind of like this right triangle that we see in the picture right here. Right? As its kind of like own little thing. And we could set up a trig ratio with angle C. If we're using the opposite and the hypotenuse, like she said, that would be the sine function. So the sine of angle C would equal the opposite over the hypotenuse. Okay? And then given that, I could write H so that it's all in terms of things that have to do with A, B, and C that are from my given triangle. Okay? Like if I multiply both sides of this by A, I have a way to rewrite H. So H could be written as A sine C. That means this formula could be 1/2, and remember my B here is not standing for base, it literally means that side that's marked B in the triangle, times the height, but the height could be A sine theta. So this could be a formula for area of a triangle that's not a right triangle. That means I could do 1/2 times 2 of the sides times the sine of one of the angles as long as they're in certain spots, right? So look at where side B and side A are. Here's side A and here's side B. And angle C is the angle between them, right? So basically, this is telling me I can calculate the area of a triangle that's not a right triangle if I do 1/2 times 2 of the side lengths, as long as I then multiply it by the sine of the angle that's between those two side lengths. Okay? Julia.
Do you do that with the side C and A at angle B, or no?
Yes. All right. So we didn't have to figure out H using angle A as our perspective, or angle C as our perspective, right? We could have used this right triangle over here and used this angle and set up a trig function over here to find H, and that trig function would have said the sine of angle A is equal to opposite over hypotenuse, which in this case would be H over C. And if you solved this for H, you would get that H is equal to C times the sine of A. So that means this formula could have been rewritten a different way. 1/2 times side B, and instead of plugging this in for H, I could have plugged this in for H. This is another formula for area of that same triangle, but look at what it's really saying. You could do 1/2 times these two sides as long as you multiply it as the sine of this angle. Look where these two sides and this angle is. Here's side B, here's side C, and guess where angle A is? Right where they meet. So there actually is even a third way to write this formula. Sorry, yes, Cameron.
Will it always be sine?
Sine in this case. There is a law of cosines too, but it works differently because cosine uses adjacent and hypotenuse. Okay? So there's actually a third way we could find the area of this triangle, still using A's, B's, and C's. Can anybody guess what the third way this formula could look like without? Good. That's another way we could have found the area of the triangle. Again, 1/2 times 2 of the side lengths times the sine of the angle between them. Now you might be like, no, Ms. Dell, that does not work from here. Well, that would require me have looked at the picture with a little different perspective, like maybe drawing the altitude one of the other directions and using a different base in order to be able to use angle B. Monet?
So when you, not really, okay, so you write the equation, does it matter if you put like B or C?
No, totally doesn't matter. B, C, C, B, they're just multiplying each other, so it's good. Okay? So this is basically kind of a different approach to the area formula. Now, you guys have done this before. In geometry, I'm sure you were given triangles where the right angle, like an angle wasn't right and you still had to find the area, and you drew in your own altitude, you figured out this, and then you found the area of the triangle. So you basically did this not packaged as a formula, just packaged as a process, right? So this formula is somewhat unnecessary, right? You could find areas of those triangles without knowing that there's this formula. You would just actually do all this work and then use the 1/2 base times height formula. Okay? So you can memorize this new formula, or you can go through all that work every time like you did in geometry to find them. Totally up to you. But my point of presenting to you this formula is so that we can then see a relationship that goes beyond just an area formula. Okay? So these are 3 formulas, but these 3 formulas calculate what? Area of that triangle, right? Okay? One single triangle, right? 3 different ways to calculate the area of the same triangle. If I put some numbers in the A's, B's, and C's spots, and you then used this formula, okay, and let's say you did this one, and then this one, would you get different answers or the same answers? Same answers, area of the same triangle, right? That means though these are 3 different ways to present it, they should all be equal to each other, and that's where we get a really cool trig relationship between sides and angles in triangles that are not right triangles. So I'll show you how that works. So Go ahead. Now you can pick up your pencil if you want. And you can write down the area formulas, okay? You might want to draw a little picture so you know what A, B, and C are referring to. But you can write down the area formulas. So, where the law of sines comes from then? Oh, yeah. Sorry, Renee. Yeah.
What was the, like, how was the last problem?
Uh-huh.
What was the question? And what is the area of the triangle?
Yeah. They would just give you a triangle. It's not a right triangle. What's the area of a triangle? So that's what I'm saying. Like, you guys can figure that out without that formula because you have geometry skills, okay? That formula is just a new way of looking at it, but the real purpose in seeing that formula specifically is to understand where this next thing came from. So the cool thing about looking at the formula and incorporating something like sine or cosine into that formula is now you've brought a trig function into a triangle that wasn't a right triangle, and you've never really done that before. Okay? So what that helps us see, those were all area calculations, right? So let's say I take two of those area calculations. And I set them equal to each other. I'm totally allowed to set them equal to each other because we just talked about this. If you did all three of those different ways of calculating the area for a triangle, they would come out to be equal because they're just three versions of the same thing, right? Let's say I want to set them equal to each other, and then I want to kind of simplify this as much as possible. What could I divide off of both sides that they have in common that could be canceled out? Cody?
1/2 an A.
1/2 an A could be divided off of both sides. Is everybody in agreement with that? Okay. So this is kind of interesting because this really narrows down some relationship in the triangle. This means side B and the sine of angle C when multiplied together equal the same thing as when side C is multiplied times the sine of angle B. The reason that's even slightly interesting is because before, this isn't a right triangle, right? There was no reason for us to bring in sine or cosine or tangent to help us figure out anything about the triangle, but now we see a relationship, okay? However, this isn't how they write the law of sines. They try to write it in a more user-friendly way. So what they then do is basically cancel all the sides out of the numerator. So I'm going to divide both sides here. Now, this is just a way of writing it, okay? I'm going to divide both sides by BC. Okay? You might not understand my reasoning of why I'm doing that, but I'm allowed to do it because I'm dividing both sides by the same amount, right? I'm really just doing it to get this idea written in a more user-friendly way. Because notice what happens here. The B's are going to cancel, and I'm going to be left with sine of angle C over side C. Okay? And on this side, the C's will cancel, and I'll be left with sine of angle B over side B. This means in any triangle, not a right, it doesn't have to be a right triangle, right? Was this stuff about right triangles? No. This means in any triangle, you can't take like the sine of angle A because you don't have a hypotenuse, but you do know that the sine of angle C divided by the side across from it should be the same amount as the sine of another angle in the triangle divided by the side across from it. Okay? Now, were these the only two area equations I could set equal to each other? No. I could do the same process again with any of the sets, right? What do you think the other ratio I'm going to come up with is going to say? Raven? Good. If I repeat this multiple times, what I'll do is just get sets of these little things equal to each other. It's going to say like sine C over C equals sine B over B. Then I'll get one that says like sine B over B equals sine A over A. And then I'll get like sine C over C equals sine A over A. Basically, any combination of them can be equal to each other, right? So this is the law of sines. So write that down, label it the law of sines, okay? And again, know what this is telling you. This is saying in a triangle, it does not have to be a right triangle. You can't set up your nice old sine equals opposite over hypotenuse ratio, but you can take the sine of an angle and divide it by the side across from it, and that should be equal to the sine of any other angle in the triangle divided by the side across from it. So that's pretty awesome because now if there's like a missing side in a triangle that's not a right triangle, if I set up a couple of these ratios, I might be able to find that missing side as long as I have the angle across from it, okay, and I'm able to use this. And we'll see how we use it in just a minute. Cody?
How would you find the sine, like if you just have the angle side before you can find it?
Yeah. So this isn't going to work in every scenario. No, you don't need every side. Let's say I gave you this. And I said, like, this is 35, and this is 12, and this is 20 degrees. And I want you to find this other side of the triangle. You could now use the law of sines to do that, right? Because sine of an angle divided by the side across from it equals sine of any other angle divided by the side across from it. That would give me an equation, a proportion, right? Where I would have the sine of 35 divided by 12 should equal the sine of 20 divided by whatever x is. I can solve that proportion. So it will not work in every scenario because there's another tool called the law of cosines. We'll talk about that in a little bit. And that's going to help us with triangles that aren't right triangles that when you set up the law of sines, you can't figure out what you want to figure out. This does require you to have at least one complete ratio, right? So you do need at least one angle with the side across from it. And then you need one other piece of information, whether it's the angle or the side, to find some other missing stuff. Okay? Now, that would be as much as I could do here. Well, actually, no, it wouldn't, because then I could add these up, subtract it from 180, and get this other angle. And I could find that other angle using the same, or the other side using the same process. Okay? Now?
So if the angle was x,
Uh-huh.
and then like the side was like 20 or whatever,
Uh-huh.
then
Yeah, you would just have the x here, and then at the end of your solving, you'd have to use like an inverse sign or something like that. Yeah, sorry. Remember, this is something we can calculate on the calculator. So you would find the sine of 35 using the calculator. Does that make sense? Okay. All right, is this okay? So now we'll see how we can use this. So we can do two things now. One thing that we could have done before, just without this formula way of looking at it, which is find areas of triangles that aren't right triangles. Okay. Second thing now, we can take triangles that aren't right triangles, and we can find missing pieces of them that we could have never found before because we didn't know if they weren't right, how to find missing sides, either using angles or something like that. Okay? So that's what this is going to allow us to do. So again, writing that formula was kind of silly if we already knew how to do it, but not silly when we then find this new ratio that exists in any triangle that can help us find missing pieces that we thought before we could only do in right triangles. Okay? Right? So the law is it's not hard to remember, right? It's like nicely packaged, right? Sine of A over A, sine of B over B, sine of C over C, okay? But there's part of this law that doesn't always work, and then that's going to be where the hard part comes in, okay? Yeah, Alex?
can have like the law of sine equal to the law of cosine.
You don't set the law of sines equal to the law of cosines. So what the law of cosines is going to do is it's going to show us a different relationship, and we're going to focus on using cosine to develop that relationship instead of sine. And so that's going to lead us to a new formula. So what we're going to have is we're going to have this one formula that involves cosines. These other ratios are formulas that involve sines. So you don't set them equal to each other, but what's going to happen is eventually I'm going to give you triangles like this and say find all the missing pieces, and they aren't right triangles. Sometimes this is a useful tool. In this problem, the law of sines is a useful tool, right? But let's say I took off the 12 and just put 15 over here. Now is the law of sines a useful tool? Because to set up one good ratio in the law of sines, you need an angle with the side across from it. So this is helpful, but can it solve every triangle everywhere no matter what information they give you? No, we would need some more tools. So the law of cosines is going to be a tool that kind of helps with the law of sines, and depending on the situation and what the setup is, we'll have to determine which one's going to be most useful in helping us find the missing information from the triangle. Okay? All right. Let's try some problems. All right, so find the area of triangle ABC if you have BC and angle A. So if you really understood the formula we just did, this now takes all the geometry fun out of it if you memorize the formula. You don't have to draw a picture if you know you have BC and angle A. You don't have to understand where everything is. You could just be plug and chug. You know how they call that once you know a formula, you just plug it in and chug it out. Okay? All right, so see what you guys get. Okay, so way number one that you could have done this. Old school. You have triangle ABC. This is how it would have been in your geometry class, right? You know that side B is 35, side C is 23, and angle A is 36 degrees. And you're supposed to find the area of this. So as a geometry student, what I would have done is I look at this and say, okay, I can use that as my base. But to use that as my base, I would need to know this height. Oh, look, from this little right triangle, I can figure out that height if I set up sine of 36 equals h over 23, okay, and solve for h. Once I know what that h number is, then I would do that the area is equal to 1/2 the base that I called 35 times the height that I get from solving that and get my answer. If I now understand how this new formula works and I like that, and that's the way I'm going to choose to do it, then I have two sides of the triangle and the angle between them, and that's enough to calculate the area. So the area is calculated by doing 1/2 times two sides of the triangle, which in this case are 35 and 23. And the sine of the angle, and the angle has to be between them, which in this case was the one they gave me, so that's why this was a perfect setup for me to use that. Okay? And then I can get my answer. What did you guys get as the area? Some sort of unit squared, I don't know. Okay? All right for the area? Okay, so now let's see how we can use the law of sine. Should I do that? Okay. Now, small warning. To use the law of sines to solve this. So if I had put this triangle up before and I had said solve the triangle, like we did yesterday, we were able to solve the triangle using trig because we had a right triangle, so we had a hypotenuse, and we could set up all those trig ratios. If I gave you guys this triangle and said solve the triangle, you could say, well, this is 100 degrees so far inside, so this other angle must be 80. And then at that point, you would be stuck because 80 is not 90, so you don't have a right triangle, and you would have no way of figuring out the side lengths of the triangle. But now, through this special version of the area formula, we have figured out that even in triangles that aren't right triangles, they have this special relationship where the sine of any angle in the triangle divided by the side across from it is equal to the same relationship of any angle side pair. Okay? So because we have this angle and the side across from it, we have one of those complete ratios. So like I know in this triangle that the sine of 40 degrees divided by the side length of 20 is equal to the sine of any other angle in this triangle divided by the side length that's across from it. So I could go and I could set I could set it equal to the sine of 60 divided by, I'll call that B because it's across from angle B, and that will help me keep it straight. Okay? Now, can I solve this? Okay, we should be able to. It only has one variable. It's a proportion, so we can just cross multiply. Okay? So B times the sine of 40 equals 20 times the sine of 60. And then I would divide both sides by the sine of 40. And then I would figure out what B is by putting all that into my calculator. So I would do 20 times the sine of 60, get that answer, and divide it by the sine of 40. Okay? What do we get when we do that? 26.9? And just make sure it kind of makes sense. All right? These angles aren't like extremely different, so 20 and 26.9 seem in the same realm. 26.9 is bigger than 20, but it's also across from a bigger angle than 20 was, so that seems to make sense.
When they say use the law of sines to solve, does that mean they just want this side or everything else in the triangle, even if you don't use it?
On your test, it will say solve the triangle, and I won't tell you whether you use the law of sines or the law of cosines. Right now, this is the only thing we've learned without a right triangle. But so that's why instead of it being like I just follow directions and use what she says, it's going to be a problem where I have a triangle. If it's a right triangle, I use the trig I know from geometry. If it's not a right triangle, then to find missing sides and angles, I'm going to use the basics I know from geometry, and when I get stuck, I'm either going to use the law of sines or the law of cosines, depending on the information given. This is beautiful information to use the law of sines, right? Because you have an angle and the side across from it, then, as long as you want something else, you can always set stuff up to find missing pieces.
But would you still want us to include the 80 degrees in our answer, even though...
Yeah, so I still want you to find the side across from the 80 degrees also if we're solving the triangle, right? They might ask you for specific things, like find side length AB, okay, or something like that. Yes?
Can you explain the second step?
This step? So I wanted to get B alone. B was being multiplied by the sine of 40, so I divided by the sine of 40 to cancel it out. And once I did it on this side, I did it on this side also.
Wait, but B was only by
Oh, I cross-multiplied to solve the proportion.
Oh, got it. All right.
Is that okay? All right, so I got B. How am I going to get C? Are we going to use Pythagorean theorem? No, because Pythagorean theorem only works in right triangles. So we have to use the law of sines again. Okay, so the sine of 40 over 20 is also going to equal the sine of 80 over whatever the side length is across from the 80-degree angle. And then I would go through the same process of solving this. Okay, so C times the sine of 40, 20 times the sine of 80. And again, I would divide by the sine of 40. And here's how I would get the value of C. What did you guys get for C? 30.6. Okay, does 30.6 make sense? Yeah, it's across from the 80, whatever. I'm just keep plugging that in because I don't want you guys to lose your common sense while you're doing the math problem, okay? We want to make sure that everything makes sense. Okay? Now, yes, this is going to get harder. So I'm going to tell you guys right now, hold on, that yesterday's lesson, you could have gone home and did anybody do homework number 1 from the, okay, yeah. So you could go home after that and do all homework number 1, right? Do not go home and try to do homework number 2 tonight. You're going to miss out on a bunch of information. Now, you can do part of homework 2. You'll see it's split into 2 pages. The thing is, this can be deceptive, okay? I know, okay? Here's why it could be deceptive. Let's say I gave you guys a triangle and I drew it like this, but are our drawings drawn to scale all the time? No, unless they tell you one way or the other, right? Okay, so let's say I draw something and I say oh, this is a 30-degree angle, okay? And yeah. Okay. I'm sorry. Okay. So let's say I drew this. And I said this was a 30-degree angle. And that this side length was 101 units long and this side length was 5 units long. Now, with the law of sines, technically we could go find this angle, right? And then we could find this angle by knowing angles in a triangle add up to 180. And then we could find the other side using the law of sines again, right? But does anything seem maybe fishy a little bit about this problem? Claire? Well, we don't know it's a 90. Yeah, so it's close, but no. Matt?
What if you multiply the angle by 100?
Okay, so he's saying this seems really long, right? For this to just be 5, true? Okay, so remember way back when to geometry when you guys proved triangles congruent, there was different ways you could do it, like ASA, SAS, right? All these ones. But then there was a couple ways that didn't work. Which ways did not prove triangles congruent? Yeah, the bad word one, right?
Angle.
Okay. Does anybody know why these didn't prove triangles congruent? Because there could be different ways of doing it, right? So these things actually don't work with the law of sines. So first of all, in the law of sines, angle wouldn't work because we need a side across from an angle to set up our little ratio in the law of sines. Okay, so that's not going to help us. But also, angle side side is a deceptive piece of information. One, just because you give me an angle aside and aside doesn't mean it actually works and builds a triangle. There are some combinations that they must build a triangle and they would build it one specific way. And that's why those worked for congruence, because if someone else was going to build a triangle with those same three pieces of information, it would be forced to look just like yours. But with angle side side, one, this might not even build a triangle, right? There's got to be a way for us to check that out. And two, let's say I made this more doable and something that we thought worked. Let's say this was 20 or something. This was 30. And let's say we knew for sure 5 worked. It could complete the distance. Okay? But let's say it wasn't 5. Let's say it's like 12 or something. 12 is definitely going to work. Okay? What if the piece is longer than this amount right here? In order to build a triangle, either the 12 could go like this, right? And it could build that triangle right there. Or I could take that exact same scenario, and if it's longer than this, the 12 could go right there and build 2 totally different triangles. Now, these both have angle side side, same exact information, but maybe the triangle can't even build, or maybe it could be built 2 different ways. Okay? So the reason, okay? So, because so many of you are going to be absent, we're going to do this lesson on Monday about how to tell if the triangle actually works before we commit to using the law of sines. I'll try to post it up over the weekend for all you field trip takers, okay? So that you can watch it ahead of time or after, up to you. But so don't go diving into your law of sines homework, because what if it's one of these deceiving situations? Just leave it alone. Let it rest in your head for a while, okay?